Everyone, we'll grab our seats and get cozy for our beginning of day 3. Hoping that everyone is feeling more or less well rested after a couple of busy days. As we officially begin our Wednesday, we would like to acknowledge the Lekwungen people, also known as the Songhees and Esquimalt First Nation, past, present, and future, on whose traditional territory we are gathering today. Our agenda today begins with keynote presentations from Allison Plourde, Andrew Clark, and Ray Landriau.
Hi everyone, my name is Lefebvre. I'm a second-year master's student at Université de Montréal. It is my pleasure to chair this final keynote presentations. So for our first presentation, I would like to welcome Allison Plourde, who's currently a master's student at Simon Fraser University. She's from Team 2, and she's going to present her work on moderating active layer dynamics with InSAR.
Thank you for the introduction. I'm Allison. I'm from the Synthetic Aperture Radar, SAR, lab at SFU. And so SAR is a form of radar remote sensing, and InSAR is a form where you can measure millimeter to centimeter scale surface deformations. And so my research is focused on measuring seasonal dynamics of the active layer, and it combines remotely sensed data with in situ field measurements. So my research takes place just north of Inuvik. I have 6 research sites. Each of these sites has one sensor that can measure vertical deformation, as another sensor that can measure snow depth. I also have these radar corner reflectors, which are essentially large aluminum triangles that can reflect the radar signal data very well. And I'm looking at RadarSat-2 radar data, as well as TerraSAR X. And so I have inclinometer data that measures this vertical surface deformation dating back to 2018 at one of my sites. And then the following year, in 2019, another 2 sensors were installed, but I'm going to focus on this red curve here at the top at Site 1. As you can see, it has this really distinctive seasonal component to it, where you can see the vertical uplift in the freezing months, followed by a subsequent thawing in the summer months. As well, there's also an apparent subsidence trend that's going on long-term at this site. And so I also have a thaw tube at this site. I only have 1 measurement from it, but from that measurement, it reports that the ground has subsided about 5.3 centimeters since it was installed in 2018, and then the inclinometer data for that same time period reported a subsidence of 6.1 centimeters. And so to provide a visual, this is what this inclinometer looks like. As you see, there is a sensor attached to this lever arm. And so as the ground moves up and down, it measures this change in angle of this lever arm. And then on the right, it has this black iron pipe, which is anchored into the permafrost. So this picture was taken in 2019, and then in 2023 at this field visit, this is the same sensor. And now you can see that this lever arm is now tilting downward. And there's substantial changes to this device. But one thing that needs to be considered here is to what degree is this actual physical subsidence of the ground, or is there any potential bias being introduced here by frost jacking of that anchored iron pipe on the right? So in 2022, I installed another 3 of these inclinometers. So the interesting thing about Site 1, it has this continuous subsidence throughout the winter months, which is not what you expect. You would expect that once everything has frozen up, that deformation is stable throughout the winter, and that's what I see at my other 3 sites. And so this presents the idea that if you wanted to measure subsidence over time, it would be beneficial to be able to do that in the winter months, where that deformation, there's less uncertainty as to compared to summer months. So just a quick thing on radar. Radar is an electromagnetic wave. It has phase and amplitude. Amplitude is a measure of how much of the signal is returned back to the sensor, and then phase is a measure of that path that signal took. And so when you're talking about InSAR, you're looking at measuring the differences in these phases between two different acquisitions. So if the ground subsided between your acquisitions, this signal would take slightly longer to get from the satellite to the ground and back up to the satellite again. And so this, you can measure the change in the deformation. In addition to that, there's a multitude of other factors that affect the radar signal on its way down to Earth and back up again. I won't go over those too much in depth, though. So to mitigate these other factors that affect the phases, why I have these corner reflectors. So they're not subjected to things like vegetation change or snow cover. In addition to that, I have the anchored reflector. And so that is supposed to be a stable reference point. So if I take the phase from the anchored reflector and subtract it from the floating reflector, I should theoretically be able to isolate just that surface deformation signal. And so a note on phase resolution, the InSAR phase is measured between plus and minus pi, and this is proportional to 1/2 of the radar wavelength. So for example, RadarSat-2 has a wavelength of 5.5 centimeters about, and so this signal will cycle many times from the path from the satellite down to Earth and back up again. But at the end, what's measured is just this slight phase shift, which is proportional to this 1/2 wavelength. And so what happens if these deformations that you're trying to measure are greater than this range, it introduces this 2 pi ambiguity to the signal. So as an example, this range in the plus or minus pi for RadarSat-2 for surface deformation is about 2.8 centimeters. So if you have deformations occurring that are greater than that, then you have to then guess these integer values of how to multiply and add a plus or minus 2 pi to your signal. And this whole process is what's referred to as phase unwrapping. And so to do this phase unwrapping, I have two methods at the moment. And so one is very basic, is just looking at the inclinometer data and picking out the points where I can see that phase wrapping may occur in the signal. And then the second method for where there's time periods where that inclinometer data may not be present, I've derived a model using Stefan equation, and from that, I'm just looking at the cumulative degree days with the caveat that this is air temperature data, whereas ground temperature data would be more suitable for this type of modeling. So these are the corner reflector results. On the right, I have in dark blue the unwrapped RadarSat-2 phase data. The black time series on the top is the phase derived directly from inclinometer measurements, and on the black time series on the bottom is the phase derived from the Stefan model. And so if you look in between the dashed lines in the pastel colors, these are the wrapped phases. And so this black time series is used to unwrap these wrapped phases to result in the dark blue time series. And then it's the same on the right with TerraSAR X in red. One thing that you can take away from this is that the phase during winter does appear to be relatively stable, so supporting this idea that if you wanted to measure long-term subsidence over time, if you could do it in the winter, that would be very beneficial. But the other major thing here is the amplitude of these seasonal measurements. They instill a lot of wrapping on this phase, and so at the end of the day, the quality of the InSAR results are only as good as the model that I've used to unwrap that phase. And then, so yeah, it brings the question, how good is my model? Am I overfitting my InSAR results to the model? And then there is also this assumption of the fact that the anchor points are stable. So the inclinometer, the thaw tube, and the anchored reflector are all anchored into the permafrost with the same method. They're drilled down about 12 feet and then filled with the sand and gravel mixture. So if there's any bias that's being instilled on these measurements from frost tracking or whatnot, that's going to occur across all of these measurements. And so possible mitigations, increasing the temporal frequency of the radar would help with this phase wrapping issue. For example, RadarSat Constellation mission now has 12-day repeat pass, and so there would be less deformation within those 12 days, and so you could get around not having the phase quite as wrapped, and that's similar to having a longer wavelength such as L-band. And yeah, increased redundancy of my field observations would help also, because all of my measurements so far rely on the same anchoring point, and so introducing methods that were independent of having that anchor into the permafrost would help. So, thank you.
Thank you, Allison. So up next is Andrew Clark. So he's from Team 4 and he's a PhD student at University of Calgary. So he's going to present his work about leveraging new technology to measure coastal erosion in the Arctic.
Good morning, everybody. Thanks for the introduction, Rose. As mentioned, I'm a PhD student at the University of Calgary under Brian Moorman, but not for much longer. My thesis is submitted to the committee. Oh, God. Stop. Defense is scheduled for January, and so now it's just kind of a matter of not tripping at the finish line. So for today's talk, I want to just kind of give an overview of my PhD work and some of the highlights of the different components, and the thesis being entitled Advancing Arctic Coastal Erosion Measurement and Monitoring Through UAV-SfM and Object-Based Image Analysis. So for some background context, we know that Arctic coast exhibits some of the highest rates of erosion in the world, and this is despite a limited open water season. Not surprisingly, this is because of permafrost and the presence of ice. And naturally, climate change is going to make this problem worse. There's going to be an increase in the open water season, a increase in the storm severity and frequency, a reduction in summer sea ice cover, leading to a more active wave regime. And what's also happening through coastal erosion is the release of sediment. In the sediment is organic carbon. When it gets released, it degrades into carbon dioxide and methane, makes its way to the coast, eventually to the atmosphere, and this represents a potentially very large source of greenhouse gas release when we consider that Arctic coast represents 30 to 34% of the world's coasts. And so all of that is to say that Arctic coasts have local, regional, and global implications, but the processes are not well understood nor well quantified. So the primary objective of my thesis was to advance this measurement by focusing on two emerging technologies, UAV-SfM and object-based image analysis. So UAV-SfM stands for Uninhabited Aerial Vehicles Structure for Motion. When we talk about mapping with drones, this is what we're doing. Basically what we do is take a series of overlapping images of an object, the coastal environment in my case, and then create a 3D representation of that. And from that we can create these really high resolution digital surface models and orthomosaics that we're able to take measurements from. Object-based image analysis is an alternative form of classification to pixel-based classification, which is very useful for high and very high resolution imagery, which can tend to get pretty noisy using pixel-based methods. So how it works is you segment an image into homogeneous regions. You can create objects of different sizes, and then there's a series of all kinds of different parameters or characteristics of those objects that you can use to classify. So I'm using these technologies to investigate along three primary themes: planimetric and volumetric quantification, multi-proxy analysis, and object-based feature extraction. The thesis is manuscript based. I have 4 papers. The first 2 are using UAV-SfM data and looking at developing all 3 of those themes. And then paper 3 and 4 is focused on using high resolution satellite imagery and just really focusing on the object-based part of it and identifying multiple coastlines using object-based feature extraction. So the first paper was a UAV technical validation. This was in part motivated because it's very easy to collect UAV data and process it, and it's kind of everywhere in the literature, but there isn't a great deal of attention given to the error sources involved. So what I did for this was created a number of different scenarios where I modified the flight pattern, the imaging angle, and then the georeferencing strategy. And in the end, the take-home message from this is that not all UAV data is created equally, and you can actually you can add oblique images to your image block to increase the accuracy of the Z direction, and this is because it mitigates the systematic error due to radial lens distortion. And my hope in this is that people using UAVs to do research will be a little bit more considerate of the data that they're collecting and then what the implications of that have on their application, particularly when you're doing volumetric calculations where it's highly dependent on the Z accuracy. So how we measure erosion is generally you have imagery and you identify a coastline or a shoreline proxy. The problem is there is a number of them, and they are kind of different from study to study. There's a number of different water lines, vegetation lines, and land features that are used. Ultimately, this will be application dependent, what coastal proxy you use to measure change, but it also is data dependent. Excuse me. So if you just kind of look at these images and reduce your image resolution, you can see that what you can identify depends on your data. And what was very common in the past when we didn't have access to as high resolution imagery as we did now, you're kind of stuck with the water line in a lot of cases, because that's the best resolvable feature. In the Arctic, though, the water line doesn't do a great job of describing the morphological changes that are happening due to erosion, because we can see that there's a number of different features found along the coast. And what I'm contending that if we want to calculate sediment release, we need to track all of these different features. And this is something that hasn't been done yet. So the idea would be to use this object-based method to extract, to get multiple coastal features. So what you would do is you start with the segmentation, and then you classify your image, and then from that you have a vectorized version of your data, and you can bring that into GIS and then pull out these different features. So how this would work in practice is you would have your shoreline proxies at time 1. This is the cliff toe and cliff edge. And then at time 2, cliff toe, cliff edge. How erosion is generally measured is using a transect method. And then you measure the intersection points of the different proxies. What we can do, though, when we have UAV data is subtract the DSMs and use these features to restrict the area of volume change to that area specifically. So instead of having just one measure of coastal erosion for a proxy that may or may not be relevant to the space, you have 2 measures in this case, and then you also, for every given transect, you have 2 measures, and then you also have the volume measurements, so you can make associations there. Where I see object-based image analysis having a real benefit is at a broader scale, where we can use satellite imagery to classify and create coastlines for large areas, and then eventually be able to monitor at a broad scale. So for this paper, I start with a single scene, and then as being the first kind of study of this kind, I tested a number of different classification methods on different image resolutions as well, so that we could understand the applicability across satellite imaging platforms. What I also did was try to iterate the parameters that go into the segmentation process to understand how the effects of under-segmenting or over-segmenting an image have on the objects you create. So this was kind of done in a way to find the ideal object size. In the end, you have these classifications. You pull out your features. Here, this is an image where the blue lines are the reference features and the red lines are the extracted features. And in a lot of cases, these lines can be right on or very close within a few pixels of the reference features, which is the general allowable tolerance for when you're trying to identify a coastline. Where it doesn't do so well is when the system is like interpreting the coastline differently than I would, or in a lot of cases, the objects that were created were just not exactly ideal for finding these features. So I took what I learned from there, and then I tried to apply it at a much broader scale so that we could understand how we might apply this technology to a broad scale monitoring program. So I looked at 3 stretches of the coast in the Western Canadian Arctic, the entire coast of the Yukon, the north coast of Peninsula Point, and then the western coast of Darnley Bay near Paulatuk. This represents, over 500 kilometers or so of coast. In this, because there is a lot more variability in the coastal environments, I had created this detailed classification scheme so that I could differentiate between land cover types that were similar but belonged in different classes. From there, I generalized those classes and then used that to extract the features, because in my case, what I was just interested in was grabbing out the boundary features between these classes. And same idea here, blue is the reference features, and then red is the extracted features. And just some samples here showing that it does a pretty good job, and it does a particularly well job in erosional coastal environments where the features are well defined. And this kind of gives a little bit more promise to the method, where if we're trying to measure sediment release, this is happening along erosional coasts. And then something else that I find that I think there's a real value in is that I was just looking at the coast, but you can segment an image and create a vector version of that, which is much more portable, and then it can be used for a number of different applications. So you're able to classify a satellite scene relatively easily and extract different measurements from that. So that's everything for me, and thank you for your attention.
It was super interesting. Thank you so much. And I can imagine how much work was involved. So congratulations on getting there. I'm curious about application and where you see, or if you see this being something that could be a tool that could be used by communities, and how complex and how transferable is it as a tool for communities?
For communities, I see it as a tool for kind of understanding what the hazards are in those areas, and then using that sort of in shoreline management. So then they can identify and track over time how their shoreline is changing and then plan based on that. I also see an application for the modelers to, support their research, where we can better quantify how much erosion is happening by looking at this at a higher temporal scale.
How hard is it for a community to use? Do they need an incredibly, is it very deep?
So, future work, in an ideal case, would be to create a system where if you have imagery, you upload it, and then it kind of spits you back this vectorized classification. and then you can use that in GIS. So, which is a lot easier to use, and with just a little bit of training, you can kind of learn how to use that as opposed to the remote sensing aspect of it. So but that's, future work that I would need some help with.
Hi, I'm John Sue from UBC. Great talk. This is really exciting work. And yeah, like mentioned, I think it's going to open up a lot of avenues for doing interesting research. My question is, can you quantify if it's consistently like either overestimating or underestimating the objects that it's mapping out?
Yeah, I think at that point you sort of have to use your judgment and use human interpretation to assess what the objects are delineating. And then based on that, you change your object parameters. There is no like how your objects are created doesn't apply from one image to the next, really. I mean, the same data source, it should be applicable, but for every time you're introducing a new data set, you have to kind of go through this iterative process to find the objects that are right for you. And then that also is dependent on what your application is. So like what I did was I started with a kind of a large scale segmentation where I would then just like filter out water and filter out vegetation. And then I did a really fine scale segmentation for everything in between so that I could differentiate between like breaking waves, wet sand, dry sand, and things like that.
Great presentation. Lots of work there. And it's really neat to see how you're using, the tools a little bit differently. I guess like moving beyond your research as a park manager, obviously we have a lot of different questions than you would as a researcher. One of the issues, like for example, on Herschel Island, we do have a lot of cruise ships that want to go there. And, a cruise ship has a lot of people and those people make a lot of impacts in an area like Herschel Island where it's quite sensitive. We have a lot of flooding of the airstrip there, just a lot of like operational problems with the changing environment. And one of the questions the managers often have is like what's going to happen in the future? Is it safe to let people go walking there? They're afraid that these things will let go and, they'll have a bigger problem. So they're a bit hesitant to, invite or allow those big cruise ships to come to somewhere like Herschel. In your research, is there any, I hate to say forecasting, but like forward looking to identifying like red zones, I guess?
Yeah, I think that's a pretty hard thing to do, strictly at using these methods because it depends on how much massive ice is in behind. So it's very hard to predict. What it can do well, particularly when you have a time series, is identify areas that are eroding, have high rates of erosion. And then I guess you can kind of extrapolate that to say, it's high here. This is potentially what the coastline is going to be in the future, but that's a very challenging thing to predict. Coastal erosion in and of itself, that's where, collaboration between different groups could potentially lead to something like that if you can map out the ground ice a little better.
Yeah, I guess that's the next step.
Yeah.
And having, just that, to me, again, it's just the idea of having your smart people brains standing on a hillside or a terrain with a park manager and just communicating in some common language. Because you're kind of looking at, similar things, but from a completely different perspective. So it's just that, how do you get it into that next level is, I guess the common problem, right? But it's neat. It's neat to see your work and what you've done there. Thank you.
Yeah, thank you for your comment.
Just a question. I know there's a lot of communities along the Mackenzie River and places that are really concerned about riverbank erosion. Mm-hmm. And have you ever tried or have folks tried using this approach for riverbank erosion and trying to look at, rates of erosion, houses need to be moved? There's a lot of issues that are front and center.
Yeah, so this was more of the open coast was looking more at the open coast, but I see it surely as applicable to that as well. It's just a matter of, getting the data and then changing the process slightly to adapt to that environment.
How much time is involved, and like what's a typical cost for doing?
Yeah. So work? I think the segmentation process is very computationally intensive. So, and this is kind of the part I like the most, is creating pipelines to process data. So you want a really good computer with good processing, and then you can also break the image up into tiles and then process it that way. So you set it up and then you kind of let it run overnight and do something else on the side, so that you can for all of that 500 kilometers or so, if everything works out well and you have it set up properly, start to finish, it could take 5 business days, something like that. But of course, there's always like, oh, I did that wrong, so I got to do it again, and it takes a little bit of time.
Have you compared it to tasked satellite imagery as well?
No, I haven't.
Okay.
Not yet. Thank you.
Thank you, Andrew. So last but not least, we have Ray Landriau from Theme 5. She's a master's student at Carleton University, and she's going to present her work on Sumps, not slumps.
A very important distinction to make, because a lot of people will call it a slump, but these are sumps. So hi everyone, I'm Ray, and like I said, I study sumps, and essentially those are drilling waste pits that are built into the permafrost in order to contain different types of waste. And the waste that I'm interested in mostly is in drilling fluids. So these were built during the peak of oil and gas in the Northwest Territories. And on the image here, you can see my colleague, Tim Ensom, holding one of our EMs. So this is the EM31 to be able to get ground conductivity readings. And so part of my work is also about capacity building. So I get the pleasure of working with the Inuvialuit Regional Corporation and the Land Administration in order to develop workshops and be out on the land with their environmental monitors to make sure that this work is continued even after the duration of my thesis. So in this image, it was a whole bunch of us that went to a sump off the Inuvik-Tuktoyaktuk Highway in winter of 2022 to do snow surveys to investigate how much snow was distributed on the sumps themselves. And you'll notice John Humphreys actually in the middle of the photo right there. Another part of my work, and really what's at the core of it, is sump assessment in order to determine if there's priorities for continued monitoring. So asking questions like, are there one or more areas that are stable, that are failing? What's contributing to this, and how do we assess this? And so what's the big deal with sumps? It's just a pit dug in permafrost. It's going to contain all the waste. But these sumps are actually the size of about a football field, which isn't small at all. And there's over 220 that we know of in the Northwest Territories in the Mackenzie Delta area. And inside of them is drilling fluids. And the devil that we know is the potassium chloride in the fluids themselves, which is conductive. And it allows us to be able to trace where the fluid is within the environment and if it's leaching out. But the devil that we don't know about these fluids is the other contaminants within them that industry does not want to let us know about. And so there's a whole bunch of different concerns that we have with sumps. The first is solute redistribution. So when you get freezing in a closed system, think about an ice cube. If you look at an ice cube, the center of it is usually white with a whole bunch of bubbles in it, because ice, when it forms, doesn't like to accommodate things in its crystal lattice. It's the exact same thing with sumps. You have freezing from the permafrost around and from the ground or from the air into the ground. And so you get the reconcentration of all of these salts, which further acts to lower the freezing point, because all of these salts were added as freezing point depressants into the fluids. Another concern is the impact it's having on the environment with the growth of vegetation. So this is Herbert Allen, who is quite a tall man, and the box around him is about 2 meters. And you'll notice that the willows behind him are still taller than him. And for context, we're standing on about 2.5 meters of snow. So these aren't small features on the landscape. The snow accumulation acts to further warm the ground surface, and it calls into question the stability of these sites. If the ground is warming, how can these fluids be frozen and contained? And especially concerning with climate change, how are these sites holding up? We have warmer air temperatures, warmer ground temperatures. Are these fluids even frozen? And that's where my work comes in. And so Chris Byrne and Steve Coquelle actually published a paper in 2009 that discussed the warming of the permafrost in this region, and it was determined that up until about 2007, the area had seen an increase in mean annual ground temperature by 2 degrees Celsius, a trend that's only continued. So today I'm going to show you 3 of my sites for a total of 5 sumps. All of these sumps are present in low-lying flat delta terrain, and they're all seasonally flooded. So they have water coming onto them. L38, which is also known as the Malik site, is pretty unique. It has 3 sumps on it, and it's present right across from Lefebvre, which I'm sure you've heard about in papers. And so that's what this site actually looks like. So the 345 L38 sump is the youngest sump at the site. It was constructed in 2002. The 2L38 was constructed in the late 1990s. And the L38 sump is the oldest at the site, and it was constructed in the 1970s. And you'll notice on all of these sites and all of the sumps present, there's ponds. And ponds are concerning for 2 major reasons. The ponds themselves in the water has a thermal influence on the ground, so it can act to warm the ground, as well as all of these ponds that are interconnected act as a highway for any sort of water-soluble components, which the KCl within these drilling fluids is water-soluble. So as soon as it gets into the ponds, it can go anywhere and everywhere. And you'll notice in the 3 images here, this is the youngest of the Malik sumps, the one that was constructed in 2002. You'll see a nice domed structure in the 2002 image, and a decade later it subsided. You'll see driftwood in the corner and ponds present throughout it. And then 10 years later, when we went back, you'll see ponds all over the place. Continued subsidence of the sump cap and water kind of everywhere. But what does this actually look like when we investigate the ground using the EM31 that Tim was holding? So we can see that the youngest of the sumps is actually holding up pretty well. Up in the center, we'll get up to the highest conductivity readings that we'll get at the site, which is 250 millisiemens per meter. The intermediate sump, which is the 2L38, has a zone of high conductivity in the center, but starts to go out towards the background. And the oldest sump at the site, for all intensive purposes, is equivalent to the background concentrations and ground conductivity readings. And so we're able to investigate and look at these measurements in a couple different ways. And one of the ways that we've done that is through these box and whisker plots. But first, I'm just going to go back. So you'll also notice that in this image, there's a zone of high conductivity of the red in between those like 2 blue blobs. And like I said, the Malik site is close to the Beaufort Sea, so it's seasonally flooded by Beaufort Sea and Arctic water. And so all of that zone of high conductivity is likely sodium chloride from the ocean coming in. And so looking at these measurements, that's why we see the undisturbed and the malic, which is in the first figure, has a whole bunch of outliers within it, and that's because of the influence of the seawater on these measurements. And it also makes the undisturbed terrain have a bit of a higher conductivity than we would expect. The oldest of the sumps, the L38, only has a difference of about 12 millisiemens per meter with the background concentration. The intermediate sump, the 2L38, has a difference about 20 millisiemens per meter. This is in the averages of the measurements that we're getting. And the youngest sump, the one that looks the most intact, has a difference about 60 between the averages. Then my two other sites that I showed you, the C42 and B19, both of which were constructed in the 1970s, have little difference between the cap and undisturbed as well. So at C42, it's a difference about 15 millisiemens per meter, and at B19, it's a difference of 2. And so what does this actually mean for sumps? And from this initial investigation, we've been able to see that the sumps constructed in the 70s look to be failing. It doesn't look like the fluids are remaining intact. The youngest sump at the site, which is the 345 L38 sump, remains to be intact. It was the one that you saw with that high zone of conductivity in the center of it. And the one of intermediate age shows an intermediate concentration, meaning that there's some stability, but it's likely to fail. And this is the B19 site, which had a difference of conductivity of 2 millisiemens per meter in the sump cap and the surrounding terrain. And you can see all the driftwood and flooding at the site itself. Thank you.
So I have a really dumb question for you.
Yeah.
Your oldest site showed conductivities similar to the surrounding terrain. Could it have been that they just didn't use salty mud back then?
I verified through all the reports, it's all saline fluids in all of the sumps. The concentrations might be slightly different, but we would still expect a similar pattern of a high zone of conductivity in the center, and then the surrounding terrain to be much lower.
Yeah, that was really great, Ray. As you know, we're doing work in the Satu region on drilling sumps in the discontinuous permafrost. But one of the things there, and I'm just curious if you've tried this, is the ERT to look at whether contaminants are actually moving off-site or just the surface water.
We haven't used ERT, just the EM31 is what we've been using, but I also took soil and water samples at all of the sites, and so those are going to be analyzed for the absolute concentrations of salts. We're just waiting on that data to come back before I can include it and stuff.
Yeah, that's great, thanks.
So I guess that maybe answers my question, but I was wondering, is this just surface measurements, or do you have, are these a measurement at a certain depth?
Yeah, sorry about that. The EM31 that we're using takes readings at 5 to 6 meters of depth, so it's the average between that. So we're getting pretty far down.
Okay, great. Because I was wondering if it was just a vertical percolation because of active layer. And what time of the year are the measurements being done?
They were done in the summer.
Yeah, and consistently all the same time, or?
Yeah. So there's past reports from like usually the early 80s into the 90s, which have an EM31 like survey of it, and those were all done in the summer as well. So part of my work for my thesis will be comparing those results with what we've collected to see how it's changed over time as well.
Okay, thanks.
Really stupid question. As somebody who never heard about sumps before, so do they have a liner? Like I might have missed it. Not at all. So
essentially how they were built is somebody went and put a whole bunch of dynamite in the ground. They blew it all up, took all of that material out, threw all of the fluids inside, put all of the stuff on top of it, said that looks at like 5 meters-ish. Hopefully that'll contain the active layer, and they walked away.
So they basically totally relied on the frozen like perimeter essentially to contain it.
Yeah, they relied on the permafrost in order to contain it. But we think that because there's like saline fluids themselves, it's probably affecting the ground's temperature beneath it and lowering freezing points, and that's like probably one way it's migrating throughout the permafrost itself. But most of my work has been done within the active layer, just because that's the part that's the easiest to get to without drilling.
So before there was the fast climate change, was this a proven procedure that actually works, or may it already not have worked then?
So most of these sites were built in the early 70s to 80s. That's like when the majority of them were built. And scientists at the time basically said, well, the permafrost is going to be frozen forever, so just put it here, it'll freeze in place. Except when you're thinking about it, they design these fluids to not freeze during drilling when encountering permafrost. So storage in permafrost didn't really seem like a great idea to me, but I wasn't around then. So
yeah, that was the question. So maybe it wasn't already a good idea back then.
No, they thought it was a good idea, but I think we've proven them otherwise.
It's worse idea.
Yeah. Okay.